Good evening, everybody. Welcome to day 21 of Math 133. Today we're going to talk about the Chapter 9 project. Um, and it's still going to be using the data from our M&Ms and our Skittles. So you're going to want to pull that up. I know we all saved it in a place that we'll remember where to find it. So you're going to need your numbers from that. Um, The Chapter 9 project is not a Google document. It is in the course pack on page 569. So you want to go get that, page 569. Okay. Um, if you do click on the Chapter 9 project in Canvas, it will bring you to a link that is going to take you to StatCrunch for the random confidence level file. So you click on that. And that's going to bring you here in StatCrunch. So you'll want to sign into StatCrunch so you can use this. But most of what we're going to be working on today is in the course pack on page 569. So, all right. So what we're going to be doing today is we're going to be looking at confidence intervals using the data that we collected on our candy from Tuesday. Does anybody have any of their candy left from Tuesday, M&Ms and Skittles, or is it all gone?
I ate mine.
So ate hers. Nice. Um, okay. So the first thing we're gonna do is we're gonna get some confidence levels. So use the StatCrunch link to generate three different confidence levels for this project. Okay. So we'll do data, sample, and then set our sample size to 3. So if you click on the link in Canvas, it'll bring you here to StatCrunch, sign into StatCrunch. And these are all a bunch of different confidence levels. So it goes from 70% all the way up to 99.8%. So you're going to pick 3 of these at random. So you're not going to choose them yourself. You're going to go to uh, stat, or no, sorry, data. It said we go to data and then sample. Okay. So we're going to select 3 of these confidence levels. So to a sample size of 3 and then hit compute. And that'll give you 3 random confidence levels. So I got 76.8, 74.3, and 71.3. And you're going to write those down here for your 3 confidence levels. Okay. Um, Mine are pretty low. I got stuff in the 70s, so that's fine. So this is a tool that you can use if you needed to do a random sample. Like, if you have a population and you can't measure that population, sometimes you'll have like millions of rows or hundreds of thousands of rows. And so this is a way that you can do a random sample using StatCrunch here. But we're just using it to select 3 confidence levels. So yours will be different from mine. Okay. So don't use the same numbers that I have here. But we're going to use this one for M&Ms. We're going to use this one for Skittles. And then we're going to use this one to revisit the M&Ms and look at sample sizes. Okay.
It gave me 74.32. Should I do it again?
No, no, no. Did you get, that's fine if you got one of them the same as, did you all 3 of them come back the same as me?
No, just the 74.3.
Oh, okay. Yeah, yeah, then you're good. You're good. Um, it is random, so technically there is a chance that you could randomly get the exact same 3 as me. We could sit here and compute the probability of it actually. We know how to do that now. But we're not gonna worry about that. So it's a very small probability. So if you do get exactly the same 3 as me, just rerun the sample. Um, because we want you to get a chance to work with data that is your own. Okay, that's the purpose of the project. So, all right. So we're gonna start with a confidence interval for M&Ms. Okay, which M&M color had the lowest count in your sample? If there's a tie, just pick one. All right. So lowest M&M for me was red. All right. And we need X, N, and P hat. Okay. Starting with N, what is N? What does that mean in this class? What does N represent?
The total number in the sample.
That's right. It's the total number of my sample. It's my sample size. So mine is 145. Okay. Um, X is for that particular data that you're looking at. I'm looking at red. So my X is 17. Okay. So yours might not be red. Whatever one is the lowest, that's what you're going to put here. P hat is X divided by N. So for me, it's 17 over 145. And I got 0.117, 3 decimal places, 117. So 11%. Um, so the idea here is that we are going to be talking about the proportion of M&Ms for me that are red. Okay, for you it might be green or whatever, but what proportion of M&Ms are red? Okay, well, my population is all M&Ms, and there's no way that I could count every single M&M in the world. Okay, so instead, I can do a sample, and I have that 11% of my sample was red. So I can use that to approximate that, okay, I'm going to guess that around 11% of all M&Ms anywhere are red. And am I right? No, I'm not right because that is based on a random sample. And we've seen that the random sample could be higher or lower than the true actual proportion. Okay. But I know that it's close. Okay. How close? That's what the confidence interval gives us. Okay. The confidence interval tells us how close we can expect to be to that true portion. Okay. And that difference is called the margin of error. Okay. So, um, anyway, uh, for this particular case, we actually know what the p value is. We know that M&Ms makes the same number of M&Ms of each color. So we actually know that there are 1/6 of all M&Ms are red. Okay. But we're going to pretend that we don't know that. Okay. Because in a normal um, uh, in a normal experiment, you can't know that. You can't know the p. Okay. So an example would be, um, let's say that we were testing some kind of new drug and we wanted to see if it was effective at preventing disease. Okay, right? Like we're testing a COVID vaccine. So we want to know what proportion of the time that vaccine works. Well, I cannot do that with a population because to test I'd have to give every single person that experimental vaccine. And not only is that dangerous, but that's also not possible. There's millions of people, right? And there's people who don't want to get vaccinated at all, right? So instead, I have to use a sample, and that is going to give me an approximate proportion that's going to be close to the true effectiveness of that drug. Okay. How close is it? That's what we're going to be talking about with our confidence intervals. Okay. All right. So to make a confidence interval, though, we have to satisfy three requirements. So the requirements for constructing confidence interval are the same requirements as the central limit theorem for proportions, okay? The central limit theorem for proportions or the central limit theorem for means, that's what's going to give us the ability to use these superpowers to actually, calculate all the kind of things that we're going to be doing in chapter 9 and 10 and 11, okay? So the chapter 9 is all about confidence intervals. So to do that, though, your sample needs to be random. Can't spell. It needs to be independent and normal. Okay. Those are the same three requirements from the central limit theorem. Now, for random, I can't just say yes, given, because nowhere on here does it say that I did a random sample. How do we know that we did a random sample? So the bag that we purchased was random, and the reason why is because, yes, because each M&M had equal chance of being in my bag, in my sample, right? So as long as everything in the population has equal chance of ending up in the sample, then that is a random sample, okay? I don't think anyone went out and was, picking and choosing the M&Ms themselves, right, to put in your bag. You just purchased a bag that was already mixed for you. Independent is you have to make sure that your sample size is not too big. For this first page, this is page 569. Um, Independent, we want to make sure that our sample size was not too big, okay? So you need to verify that your your lowercase n, your sample size is less than 5% of the population, okay? Or you can do it as 20n is less than capital N, okay? That's the one I'm going to be using here. 20n is less than n, okay? I don't think any of you guys went out and bought 5% of all the M&Ms in the world. There's nobody, yeah, nobody has that much money, right? So, all right, 20 times my n was 145. Okay, that in your calculator is 2900. Okay, is that less than n? Well, what is capital N? So my lowercase n is the sample size. I had a sample of 145 M&Ms. What's capital N?
All the M&Ms in the world.
That's right. All M&Ms. So uh, is 2,900 less than the number of M&Ms in the world? Yeah, it's way less, right? So yes, definitely. Okay. So independent is usually not the one that's an issue. It's this one here. It's normal. We need to check to make sure that our sample size is big enough. Okay. So for means, we would be looking at, we need to make sure that our n is bigger than 30. Okay. My n is bigger than 30, but I'm not looking at means. I'm not looking at like the average height of all the people in the US. I'm looking at the proportion of M&Ms that are red. So for proportions, you need to check that N times P times Q, that has to be bigger than 10. Okay. So for me, I have 145. My P value is 0.117. My Q one minus 0 is 0.883. Now yours is going to be different from mine because your N is different. You had a different size bag, you had a different proportion. Okay, that's fine. So calculate our math here. 5 and I get 14.98, so pretty much 15. That is bigger than 10, so yes. So mine was big enough. My sample size was good. Uh, what about you guys? After you do N times P times Q, did anyone get less than 10? So Mark got less than 10. So in his case, his answer is no. So what does that mean? Well, that's fine. I'm not going to mark you off for no. It just means that your sample size was not big enough. I'm certainly not going to make you go back and buy more M&Ms or anything. Um, but what's going to happen is your results are not going to be as reliable. Okay. So since you don't have all three as a yes, that means you're not allowed to use the central limit theorem, which means that your confidence interval is not going to be accurate enough. Okay. And that's important when we are, presenting this kind of result to like business leaders or a boss or something like that. Okay. We need to make sure that we can say that it is accurate. Right. Anyway, let's move on to the next page, page 570. And so you'll see for question number 4, regardless of whether or not the requirements were met, we're going to push on forward and construct a confidence interval for the proportion of M&Ms that are your color. Mine is red. Okay. So we need to show the formula, substitution, and the result. Okay. Now, before we go on, so my p-value was 0.117. Mine is 11%. So I'm approximating that 11% of all M&Ms are red. Okay. So is that accurate? No, it's not. Okay, but it's close. How close? That's what the confidence interval is going to give me. But we actually do know what the true proportion is. We know that there are 6 colors and they make an equal amount of each. So we know that 1/6 of all M&Ms are red. So 1/6 as a proportion is 16.6% or 16.7, 0.116. Okay. So you can see, like I said, my number is not 0.1666. Yours is probably not either. Okay. That's okay. So when we're building the confidence interval, we're hoping that 0.1166 is somewhere in that interval. Okay. Maybe it will be, maybe it's not. Let's find out. So first of all, the formula for this, you'll find that on page 259. And there's a couple of there's two. There's um this one. Oh, sorry, that's not right. That's page 260. I'm looking at the wrong thing. Page 259, confidence intervals. So there's two. There's a confidence interval for a proportion, and there's a confidence interval for a mean. And they're very similar to each other, and that's why we're covering them both in the same chapter. But since they're similar, you have to pay attention to which one you're supposed to be using. It's usually obvious whether you're looking at means or proportions, okay? And most of the steps are very similar. But anyway, we are going to be doing proportions. So our formula is right here. It's p hat plus or minus z alpha over 2 square root p hat. So this whole crazy thing, okay? Basically what we're doing is we have a point estimate for p. We're estimating that the true p-value is p hat, 11%, okay? but we're off by a bit. We're off by what's called the margin of error. So margin of error is all this extra stuff over here. Okay. So our formula is p hat plus or minus z alpha over 2, big square root, p hat, q hat over n. Okay. Our substitution, we just plug in what we have, okay, plus or minus. Now I'm going to leave some space here for my z alpha over 2. I got to go figure out what that is. My Q is 0.883. My n value is 145. So now we need to figure out z alpha over 2. Now, we're going to use the confidence level from number 1, okay? So we have these 3 different confidence intervals. This one's going to be for M&Ms. This one's going to be for Skittles. And then this one's going to be back for M&M sample size, okay? Which we'll do on the last page. So starting with M&Ms, I'm going to use a confidence interval of 76.8, okay, or 0.768, okay? That's my confidence interval. So I'm going to use that in StatCrunch here. I need to get a normal curve. So that's under Stat, Calculators, Normal. Stat, Calculators, Normal, okay? You can also do this under Stat, Portion Stats, One Sample with Summary, okay? I'm going to start with the Stat, Calculators, Normal. I know that's a little different from what Cindy might have shown you, but I want to start with this because it's much more visual, okay? So here's my normal calculator, and I'm going to do between because I want to find a range of numbers between for my result. My confidence interval is going to be 2 numbers, a lower end and an upper end, okay? So here's my lower end, here's my upper end over here, okay? The red part in here is going to represent my confidence interval. The white part on the outside, that represents alpha. Alpha is not my confidence interval, that's my error, okay? And it's alpha over 2 because there's 2 sides, there's 2 white parts, okay? Anyway, all I need to do is put my confidence level right here. My confidence level for number 1, I'm using 0.768, okay? And it's going to say that my z values are these, 1.1952, okay? 1.1952. Now, there's a +1 and there's a -1, and that's why there's a plus or minus, okay? So your Z alpha is going to be different because you have a different confidence interval, confidence level, okay? That's fine. Once you plug those in, you can either do this in Desmos and get your result. You'll have a lower end and an upper end. Or you can do this in StatCrunch. And I'll show you both tonight. I'm going to start with Desmos. So here it is, and I'm typing in my numbers. Here's my p-value. I'm going to start with the minus. I'm going to start with the -1. 1.1952 times SQRT. Da, 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 divided by 40. Okay. So my low end is 0.0851. Right? So all I did was I plugged all this in using a minus sign. I need to do the same thing, plugging all that in with a plus sign. So I can just go up here and change this minus to a plus. And now I get the other end, 0.1489. All right. And that's my result. This is my confidence interval. Okay. So this is the confidence interval for my confidence interval was 76.8%. Okay. You don't need to know that, but this says that I am 76% confident that the true population proportion for red M&Ms is somewhere in this range. Okay. So it's not 11, it's not 0.117, but it's close. It's in this area. Okay. Now, is it actually? Well, I'm not 100% confident. I'm only 76% confident. That means there is a 24% chance that I'm wrong and that the true population proportion for red M&Ms is outside this range. Okay. We're never going to be 100% confident. The only way to be 100% confident is to check everything in your population, which we can't do. We cannot check every single M&M in the world. Okay. So we can never be 100%. And that's the whole point of doing a sample is you can't measure the population, so you can measure it using a sample. Okay. Um, you can now normally 76%, that's a very low confidence. A 24% error rate, that's pretty unacceptable. Okay. A normal confidence level would be 95%. That is the most used one. Okay. And 95%, we've talked about it before, is an important one in this class because it's where it's the cutoff where we consider things unusual or not. Okay. But you could go higher. You could say, I need a confidence interval. I need to be 99% confident. There are some times that you can be 90% confident and still make the right business decision. So I don't usually feel very comfortable going below 90. Okay. You could be 99.7. 99.7, we know that's 3 standard deviations out, and that's pretty confident. Okay. There's some rare cases that you need to be extremely accurate. Okay. 99.99-ish. Okay. But that's usually like we're talking about, medical situations, life or death stuff. So anyway. So Willy Wonka claims that the proportion of candies of my chosen color, red, is actually less than 1/6 in any bag. Okay. Does my confidence interval support his claim? So he is saying that there's something shady going on at the M&M's company, and they're making less red than they should be. Okay. Maybe red dye is more expensive or something. Okay. So my confidence interval right here is 0.117. Okay. That's my p hat. 0 point, and you don't need to draw this, by the way. This is just a visual so that we can, understand what's happening here. 0.085 is there, and then 0.1489 is there. So my margin of error is this right here. And so if you go up by the margin of error or down by the margin of error, I get this range here. Now, we know that the true value is 1/6. 1/6 is 0.1667. That's actually here, 0.167. That is outside of my range. Okay. So in this case, the true value is not in here. I said I was 76% confident that it would be. Well, in this case, I was wrong. Okay. So in this case, I support his claim because my entire interval is below 1/6. Okay. Um, but there is a 24% chance that I'm wrong, and that's what's happening here. Okay. Now, did anyone have a confidence interval that actually did include 0.167? 1/6 was actually in your range. Yeah, so Ivana had that actually the 1/6 was inside the range. And so she would circle this one. She does not support his claim because 1/6 is close enough to her estimated p hat. Um, And so you can't really he can't, don't agree with him that he's saying that it's less than that. Okay. Anyway, those are the two possible answers depending on what your confidence interval looks like. Okay. Now, um, suppose that we had used a much bigger bag, okay, with thousands of M&Ms. So let me ask this, Ivana, your 1/6 was in that range. What was your N value? How many M&Ms did you have?
146.
146. So you were right around mine, okay? What was your confidence level? Mine was 76%. What was yours? Ivana, what was your confidence level for number one?
Sorry, it was 86.3.
Yeah, so your confidence level was higher, which meant your confidence interval was actually wider than mine. Okay. So yours would have been like this and would have actually included the 1/6. Okay. Okay, so suppose that we had a super big bag with thousands of M&Ms in it. Mine only had 145, Ivana's had 146, but the proportion was still the same, so still 11% for me. Uh, the confidence interval that I would create from this bag, would it be narrower or wider? Okay, so the way that it's best to think about this, in my opinion, is a larger sample size means you will be more accurate. Okay. That's the way I like to think of it. So the bigger your sample size, the more accurate you're going to be. So if you had used a bigger sample size, you would have been more accurate. So more accurate means you would have been closer, narrower, you would have been closer to the actual result. Okay. Um, so it's this one, narrower, because the sample size and the error have an inverse relationship. So everyone's circling that one. Over here, it depended. Um, this one, we go with that one. So the way we'll revisit this, we're going to get a chance to talk more about these. But the easiest way to remember it, in my opinion, is larger sample size means you're going to be more accurate. Okay. And by more accurate, I mean I want to be as accurate as possible. I don't want my margin of error to be large. I want my margin of error to be small. So I want a small range, a small confidence interval. That means I'd be more accurate because think about it like this. Uh if I was trying to be accurate and I said, well, and I give you a giant range, it's not very useful. If I said that the average height of people in America is somewhere between 3 feet and 8 feet, that's a huge range. That's not helpful at all because someone who's 3 feet is very tiny, someone who's 8 feet is very tall. I want to know what the average height is. Well, it could be anywhere in there, right? On the other hand, it would be much more accurate, it'd be much more reliable, much more useful if I could say that the average height was somewhere between 5 feet 4 and 5 feet 8. Okay. Then I'm like, oh, that's a pretty tight range. Okay. All right. So that's that. That's it for M&Ms. Let's go to page 571. We'll talk about Skittles. Which Skittle color had the highest value in your sample? Which one did we have the most of? All right, so Skittles, I had the most of yellow. Oh, of course, that's the one I don't like. There's there's a conspiracy there. X for me was 55. My N was 241. My p hat is x divided by n, which is 55. Oh, whoops. 55 divided by 241. 0.228. All right. Verify whether all the requirements for constructing a confidence interval for the portion of this color of Skittles is satisfied. So same thing as before. We need to verify that it is random, independent, and normal. Okay. So same thing with Skittles. This is random because every candy, every Skittle had equal chance of being in my bag, right? Being in the sample. Okay. So independent, I need to check 20n is less than capital N, so 20 times 241. For me, that is 4820. And that is that less than all Skittles? Yeah. There's way more than 4,800 Skittles, so yes. Lastly, you need to check N times P times Q. 241, 0.228. My Q is 0.772. 241 times 42.4, and that is bigger than 10. So yes. Okay. So when you're doing this check for n times p times q, I could have written it as p hat times q hat because we don't technically know what p and q are. I mean, we do, right? Because we know that Skittles makes the same amount of each color, but like I said before, in practice, you're trying to figure out P, you don't know P, and you can't know P with perfect accuracy. Okay, that's the whole point of doing the sample. Okay. Um, but when you're doing these, it's important to make sure that you pick a big enough sample size so that your results are reliable. So for means, you can pick a number as long as you're picking n is bigger than 30. Um, but for proportions, it's not just the n that matters. You have to check p and q as well, because I could pick a sample size of 1,000 and it's still not big enough if my P is very small. So an example would be like if I was an ad company and I was trying to see if I should run this ad to see if, is it going to be effective? Well, I don't want to have, pay millions of dollars for the Super Bowl commercial that's not going to work, right? So I could run a sample, okay? And I could get like 1,000 people and show it to them and see if it's if it works. I could show it in a small market, right? But the p-value for advertising is tiny. Okay. Think about all the commercials you see. How often do you buy something because of a commercial? Do you buy something every time you see a commercial? No. Do you buy something 10% of the time? Definitely not, right? That would mean that you would see 10 commercials and then buy something, right? Most of the time, the success rate of a commercial is less than 1%, right? You have to see more than 100 commercials before you're actually affected to the point that you buy something. Probably even more than that, right? So if your p-value is 1%, 1,000 times 1% is only 10, and that's not big enough. It needs to be bigger than 10, okay? So, yeah, so when you have tiny p-values, your sample sizes really get big quickly, okay? Or need to in order to be accurate. All right, so let's go to question 9, page 572. Regardless of whether or not the requirements were met, construct a confidence interval for our Skittles. This time we're going to use confidence level number 2, okay? And we still are going to show the formula. We do the substitution. And we get a result, okay? And the result is going to be two numbers, a lower number and an upper number, okay? Page 259. P hat plus or minus is alpha 2 big square root p hat q hat over n. All right, so my z alpha over 2. So this time I'm going to do it in StatCrunch. But instead of using this normal calculator so it's more visual, I'm going to show you how to do it with the proportion stats. So we go to Stat, Proportion Stats, one sample with summary. Stat, Proportion Stats, one sample with summary. Okay. Number of successes, that's our X. I had, how many Skittles did I have? 55 yellows out of 241. There's a button here to click for confidence level, and you have to tell it your confidence level, which was from number 2. Mine was 74%, 74.3. I'm going to compute. Okay. Oh, and where's my Z alpha? Where's my Z alpha? Ah,
You have to tell it to include
yeah,
critical value.
yeah, that's right. Portion stats. Now I gotta do it again. Yep. Show me my critical value. There it is. My critical value in this case, 1.1335. Okay. So 0.228. 772. Okay. So in StatCrunch, if you do stat, proportion stats, one sample with summary, yep, don't forget to select that button. Sorry about that. But your lower limit and upper limit are right here for us. 0.1976 and 0.2589. At least that's what I got. My numbers are, okay? If you do it in Desmos or StatCrunch, either is fine. You will get slightly different answers, and I will accept either of those. The reason why you're going to get slightly different answers is because we rounded this, right? It was not actually 0.228, it was 0.228215, blah, 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 blah. It's not actually this Z value, it's this one, and this decimal even keeps going, okay? So when you do it in StatCrunch, StatCrunch doesn't do with any of the rounding. So since it's not rounded, it's slightly more accurate. But I'm not going to mark you off if you use either of those. Either way is fine, okay? All right. Willy Wonka's bothering me again and claims that the proportion of candies of my chosen color is more than 20%. So 20% is 1/5. There are 5 Skittle colors, so we know that 1/5 of all Skittles are yellow. He is saying that actually there's something weird going on. They don't like you, Joe, so they're making more lemon than 1/5. Okay. Do I believe him? Well, is 20% in my interval? So right here's 0.197, here's 0.25, 0. So this is my confidence interval right here. So I'm 74% confident that the true proportion of yellow is somewhere in this range, and it is in this case 0.20 is in that range. So in that case, I don't believe him, okay? Because 20% is in my range. Now, if 20% was down here, I would support him because my entire interval would be up above 20%. So those are the two possible answers for number 10, okay? All right, question 11. Suppose when creating the confidence interval for here, instead of using 74%, so instead of using this one, what if I'd used confidence level number 1, okay? Would my resulting confidence interval have been narrower or wider? Well, it's going to depend on which of these numbers is bigger for you, okay? So for this case, my number 1 was slightly larger than my number 2, okay? So since my number 1 was bigger, it was more accurate. This one was more accurate. This one, on the other hand, was slightly smaller, okay? So would it make it narrower or larger? So if your number 2 was smaller, okay, then what's going to happen is if you switch to a larger confidence level, you're going to get a larger confidence interval. Larger confidence level means larger confidence interval. Okay. Now, on the other hand, if these had been switched, or if you had, let's say this one was 80% and this one was 95%, if this one is bigger, this one's going to have a larger confidence interval. So you'd have it be narrower. So one of these two answers is the one you're going after, okay? Right? Because like if I was looking at, so this was my resulting confidence interval for 74.3%. If I was looking at a 95% confidence interval, we know the z-value for that is 2. And so you can see that it's much wider. If I'd been looking at 99%, that red area is very wide. Okay. So a bigger confidence interval is going to mean, or level is going to mean a bigger confidence interval. All right. Our last page is page 573. Calculate the minimum bag size required to ensure that the proportion of your M&Ms is within 2% of the true population proportion for that color. Use confidence level number 3. So now we're going to use this guy, minus 71. Use confidence level 3 and assume you do not have a prior estimate. Let's show our formula. Do some substitution. And get a result. Okay. This formula is on page 261 in our course pack. So still in our yellow exam notes packet, so page 261. And there's three here. Or no, I guess there's four. There's for the proportions, and then there's also for means. Okay. We're doing proportions. Okay. And it's going to depend on whether we have a prior estimate for p hat or if we have no clue. Okay. So an example of this is let's say we were trying to figure out how big of a sample size we needed to measure something, and we wanted to say like um what percent of the people in the US have a what percent of them have an STD, right? I have no clue. I is it 1%? Is it 10%? I don't know. Okay. So in that case, I would have no prior estimate and I'd use this formula. Okay. Now, if you've run the experiment before and you weren't happy with the results, you might have a prior estimate. So for example, with the M&Ms, when I was doing the M&Ms, I ended up having that 1/6 was not in my confidence interval. Okay. So that means that I was wrong, right? So that's no good. So that must mean that my sample size was not big enough. A bigger sample size will make it more accurate. So what sample size do I need to be more accurate? I want to be within 2% of the true population. The true value was 16%. So to be within 2%, I need to be somewhere between 14 and 18. Okay. So using no prior estimate. I know we do have a prior estimate because we already did it. So it doesn't make sense to use this formula, but just go with me for the moment. Formula is n equals 0.25 C alpha over 2 over my margin of error squared. Okay. So how big of a sample size do I need for a 2% error? And I need to get my Z alpha over 2. Now, what's my Z alpha over 2? I want to use this confidence level, 71.3. So in stat calculators, normal, I'll put in my 71.3. My Z value is 1.0647. All right. So what's my result? N equals 0.25 times parenthesis. Close my parenthesis. Hit the Shift 6 button to make it an exponent. I need 708.49. Okay. So I can't look at 708.49 M&Ms. 0.49, I mean, I guess you could cut an M&M in half, but it doesn't make any sense. This needs to be, when you're doing a sample size, it always needs to be a whole number. But we're not going to round this like normal. We are going to always round up. Okay. So even though normally I would write this as 708 because 0.49 would round down, I'm going to round up to 709. Okay, 709 M&Ms. It's a lot more than I had before. I had 145. And so by using a larger sample, I'll be able to be more accurate. Okay. And sometimes it's okay to start with doing a small sample and then do your large sample. Okay. And that's because you can get a prior estimate. We actually have a prior estimate. So this one didn't make any sense. It would have made more sense to use our prior estimate of P when I had the 145 M&Ms. Okay, so we'll do that in a second. But so we always round up when we are talking about sample sizes. We always round down when we're talking about percentiles. Okay, other than that, we're going to round normal in this class. Suppose when completing number 14, instead of using a 2% error, I'd used a 1% error. Would my sample size need to have been bigger or smaller, larger or smaller? So I said that with a 2% error, I needed to be somewhere between 14 and 18%. A 1% margin of error means, well, the true value is 16. I need to be somewhere between 15 and 17. I need to be more accurate. Okay. So that means I need a larger sample size. A 1% error rate is much more accurate than a 2% error rate. Okay. So larger sample size can be more accurate. All right. Let's do calculate the minimum bag size again, same confidence level and error rate as number 14. So 2%, same thing, but this time use your p hat. So this is what we should have done, okay? Because we actually did have a prior estimate. All right, so n equals p hat q hat. Oh no, not square root, square. Dang it. It's this guy. Okay. P hat q hat. Page 261. All right, so 0.2, no, sorry, M&Ms. We're doing M&Ms. 117, 0.883. Z alpha over 2 is the same here. Okay, so you don't have to go back and redo that because we're going to keep the same error rate, 0.02 squared. Now, I know that there's a lot of proportions flying around. We have margin of error of 2%. We have a confidence level of 71%. We have a p hat of 11%. We have a p value of 16%. So I know there's a lot of proportions flying around. So it can be hard to keep track of everything. So your margin of error is small. Okay. Your confidence level is large. A normal confidence level is like 95%. Alpha is the opposite of net 95%. So it would be 5%. Or in this case, 71 is my confidence level. So my alpha is just the opposite of that, which is 29%. Okay. So I know it's hard to keep track of all of the different proportions and stuff. So practice is the way to go. So I've got 0.117. We'll get a chance to do more of this practice on Tuesday when we look at the Chapter 9 review. And I need a parenthesis 10647. Divided by 0.02, close my parenthesis, square it. All right, so 274.9. And I'll round that one up, which I would have rounded up anyway. So n equals 275. Okay. So if you have a prior estimate, you don't need quite as many. It's a little bit smaller. All right. Lastly, of the 3 confidence levels, so here's my 3 confidence levels that I had at the start. Which one would yield the largest sample size? So largest sample size would be the most accurate. So which of these 3 is the most accurate? Number 1, yep. For me, it's number one. For you, whichever one of these is the highest. Whichever one is the highest, that's the one you're going to circle, okay? All right. That's it for our Chapter 9 project. So make sure you submit that in Canvas. If you have any questions on anything, feel free to stick around. Otherwise, have a good weekend. And don't forget to do your lecture notes.